Hi guys, Miss O'Connell here again. So this is video 2 for constant acceleration kinematics. So again, we have our big four equations. We've learned how to find displacement from a situation in which the car accelerates at constant acceleration, whether we are given that acceleration or not. In that video you watched earlier, you're able to find the velocity, the final velocity of an object in which it accelerates at a constant rate. What we're going to now discuss is the last set of examples in which you can find displacement after any velocity. Okay, so we're going to take a look at the last two examples on the constant acceleration kinematics packet. Okay, so again, primarily we're going to use the equations that involve velocity. Okay, and in terms of delta x. So have you guys turn to that section of your packet, to that first example, after velocity, after any displacement. Okay, so example 1, a person pushing a stroller starts from rest, uniformly accelerating at a rate of 0.5 meters per second. So they give us this constant acceleration rate. We know that's the acceleration because of the units, meters per second. Part A asks, what is the velocity of the stroller after it has traveled 4.75 meters? Okay, so you can draw our nice diagram of person pushing a stroller, and we're going to label our givens. So our initial velocity, v sub naught, is 0. Okay, the stroller starts at rest. Then begins uniform acceleration. A equals a positive 0.5 meters per second squared. We're looking for the final velocity. We know that the displacement, delta x, is 4.75 meters. Again, you can use any two combinations of equations, and as long as you plug in the right variables and manipulate the equation algebraically, you will get the correct answer. But we technically have initial velocity, acceleration, change in displacement, or change in position, and we're looking for a final velocity. So the easiest equation to use here would be most likely equation 3. V squared equals VO squared plus 2 times A times delta x. So we're going to plug in what we know and leave what we don't know as a variable. So I'll have V squared equals 0 squared plus 2 times 0.5 meters per second squared times 4.75 meters. So the right side of my equation is going to simplify. I have 2 times 0.5. I'll get 1 times 4.75 meters. I get 4.75 meters. Meters squared over seconds squared. Okay, so how that occurs, right? I have meters times meters divided by seconds squared. To get v by itself, I'm going to take the square root of both sides of my equation. V squared, we just get v. We take the square root of 4.75. We get 2.18, rounding to the 100th place. Square root of meters squared is simply meters. Square root of 1 over seconds squared, I get seconds. So the final velocity of the stroller, I have 2.18 meters per second. Okay, so not too ridiculously unreasonable for a walking velocity. But let's take a look at now when the stroller travels 6.32 meters. Okay, so same general situation. The givens that we can use, okay, we can keep our initial velocity. We have the same acceleration rate, but my delta x value, our displacement, is now 6.32 meters, which means that more time has passed. Okay, more distance has been traveled, more time has passed, so we're going to have a different velocity. Okay, thinking about this situation, do you think that the velocity should be larger or smaller? Okay, so hopefully we get larger, right? Because our acceleration is positive, our velocity is positive. The object should be speeding up in the positive direction. So when we solve for v, we should get a positive value that's larger than the velocity from part A. So I'm going to use that same equation here, v squared equals vo squared plus 2 times a times delta x. V squared equals 0, that's the initial velocity, plus 2 times 0.5 meters per second squared times 6.32 meters. So again, same steps here. I'm going to plug that into my calculator. I get 6.32 meters squared per second squared. Take the square root of both sides. I get 2.51 meters per second as my final velocity. Okay, which is considerably fast. So this person is like sprinting with this stroller. Okay, but physically possible, but a little ridiculous. So hopefully after 6.32 meters, they stop pushing this stroller. Okay, so let's take a look at example 2.